Hi, this video is about kinematics equations. Welcome to maybe the hardest part of this class all year. So let's talk about some equations that we can use to describe motion using all of the principles we've already learned. Here we have an object that's speeding up from 2 meters per second to 6 meters per second. A question we could ask is, what's the average velocity? That may not be a question that you ever wanted to ask, but now you know the answer. For a uniform acceleration like this, where it's staying constant throughout, it's a straight line, the average velocity is simply add up the starting and the final velocities and divide by 2. It's just like you would find the average of any two things. You add up the beginning and the end and divide by 2. So in this case, 2 plus 6 divided by 2 is 4 meters per second. So that would be the average velocity here. Note that this average velocity equation does not apply to non-uniform acceleration, which only means that if you speed up real quick and then you go at a high speed for the rest of your travel time, you can't just say initial plus final divided by 2 because you spend a lot more time in the final velocity than you did in the initial. It only works if you're uniformly accelerating. You're increasing your velocity by the same amount each second. So this is our first of our new kinematics equations. Let's do some examples with that equation. Let's say an owl spots a tasty squirrel in a tree while flying at 2.2 meters per second. The owl attacks and reaches a speed of 5.7 meters per second in 1.5 seconds. So it speeds up for the attack. What is its average speed and how far did the owl travel? So we have two questions. First question, what's the average speed? So I always identify the things that we have been given in the word problem. What do we know about the owl's motion? We know it had an initial speed of 2.2 meters per second and a final speed of 5.7 meters per second. It also gave us the time of travel, the time of acceleration, I should say, which was 1.5 seconds. The first question is, what's the average speed? So we're going to use that new equation that we just saw. Average speed is you add up the two initial and final speeds and divide by 2. I'm saying speed and velocity as if they're interchangeable. Just know that I am talking about velocity here. I've indicated that with the vector symbol. So we are including direction, but sometimes I just say speed because in this case, the direction doesn't make much difference. You add up these two, 2.2, 5.7, you get 7.9 divided by 2, and the average speed or average velocity rounded to two significant figures is 4.0 meters per second. So what about how far does the owl travel? It's speeding up, so it's not so simple as just like our typical equations in the past, because it's changing its speed, but how do we find its distance? Well, we can use a faithful old equation to do this. We have the same three pieces of info as before, but now we add the average speed we just found was 4.0 meters per second. So we're looking this time for how far, which is the change in position. How much distance does it cover? So the change in position is the unknown. Now, if you look back at some old equations, we're going to try to find one that has the delta x in it, but it includes some of these other pieces of information as well. We don't necessarily need them all, but we need to be able to solve for delta x. So we're going to use this old equation here. The average speed is the displacement over time. We can rearrange it a little bit by just multiplying both sides by t, and that gives us our displacement is the average speed multiplied by the time. So knowing our average velocity is 4 meters per second, we can multiply by 1.5 seconds and get a displacement of 6 meters, 6.0 meters. All right, let's look at another equation. Now, I will warn you, this is a little scary when you first see it, but stay with me. One of the questions we can ask is, what if we don't have the time that an object was traveling, but we do know it was accelerating, and we want to know what its final speed is after it accelerated a little bit, and we also know how far it traveled. So like the owl in the last example, we know how far the distance was. We didn't have a stopwatch. We weren't able to get the time, though. Can we somehow find the final velocity? So to do this, we're going to derive a new equation. And when I say derive an equation, what I mean is we're going to come up with a new equation using previous knowledge and equations that we have. We can put them together, and through a little bit of algebra and some logical reasoning, we can come up with a new equation. So we're going to do that with these two equations that we just used on the last example. The average speed is the displacement over time, and over here, the average speed is the initial and final velocities divided by 2. So we can put these two together, because if they're both average speeds right here, then these two things are also equal. And so that's what I've done here. I put the two other parts of the equation together and set them equal to each other. They're both representing average speed, average velocity. So doing that, I'm going to take these two sides of the equation, and I'm going to do something a little weird. I'm going to multiply both sides by acceleration. On this side, I'm going to multiply by a for acceleration. But on this side, I'm going to multiply by what acceleration is equal to, which is the final velocity minus the initial velocity over time. So doing that gives me this long mess here of terms. So I have acceleration, displacement over time, and then I have these two multiplied together divided by 2t. I want to get rid of the fractions if I can, so I'm going to multiply by 2t to kind of undo this. That cancels out the 2 and the t. Over here, I also multiply by 2t. But look, I have a time in the denominator over here as well, so the t's cancel out. We get rid of time altogether. So the time has been removed from this equation altogether. What we're left with is 2a delta x is equal to vf squared minus vi squared. After we multiply these two together, we're left with final velocity squared minus the initial velocity squared. One last step, we're going to move the initial velocity over to this other side here and then flip the equation so that we have a new equation. The final velocity squared is the initial velocity squared plus 2 times the acceleration times the displacement. So in this equation, we don't have time at all, but we're still able to find an object's speed after accelerating if we know the displacement and the initial velocity. So let's look at an example like this. Almost dropped the whole thing. I just dented the wall. Okay, that's all right. So let's say a fighter jet attempts a landing at an aircraft carrier, starting at a velocity of 64 meters per second and slowing down at 30 meters per second each second. Will it stop before running off the 100-meter runway? So for this problem, we have our given information as the initial speed is 64 meters per second. The acceleration is negative 30.0 meters per second. Our displacement is what we want to know, because we want to know, is it going to stop in time before it falls off? And stopping in time in this case means 100 meters of distance. Is it going to stop before the 100 meters, or is it going to go past that 100-meter mark? So we want to know what is the plane's actual displacement, and we're going to compare that to see if it's under 100 later. So we have initial velocity and acceleration. So this equation seems to be the right pick because we're looking for displacement. We have these other two, but what's the final velocity? I'm going to hover over this so you don't see it. What is the final velocity? Well, look back at the equation. Look back at the word problem. And there's a clue in there that tells you the final velocity, and it's this word right here, stop. So a lot of times there's hidden pieces of info in the word problem itself. We're looking for a final velocity of 0 because that's what it would mean to stop, right? So we need to say over here, we're going to say that the final velocity equals 0. So now that we have that out of the way, we're able to plug in 0, substitute in these other numbers here. 64 gets squared, 2 times negative 30. So we're left with 4,096 meters squared over second squared minus the 60 times delta x. So we can't do the subtraction yet because the 60 is being multiplied by the delta x over here. So I'm going to move this whole term over to this side of the equation, get rid of my negative sign here. So I'm going to add 60 times delta x to both sides. So I effectively move it over. I have 60 meters per second squared times delta x is equal to 4096 meters squared over second squared. I'm going to solve for delta x, so I'm going to divide by the 60 meters per second squared on both sides. That'll cancel out everything but the delta x over here, and we get 4096 divided by 60 is 68.3, and then the units, They're almost identical, except we have one extra meter up here. This is meter squared. So everything else but the extra meter cancel it out. So we're left with meters for our unit. 68.3 meters is the displacement of the fighter jet. So does it stop before falling off the aircraft carrier? Yes. It stops in 68 meters instead of 100 meters. So the jet stops in time. So that's all I've got for you in this video. Remember, everything you have is a gift.